these equations are given as m1 x2 double dot plus b1 x2 dot plus k1 plus k2 all times x2, and that's equal to k1 x1 plus k2 x3. Let's label that equation 1. The second equation is m2 x3 double dot plus b increment times x3 dot plus k2 x3 equal to k2 x2. Okay, this b increment is just a coefficient we use to represent the nonlinear function after we have linearized it, but in this case we can just represent it with b increment. Alright, so there are actually many ways you can approach draw this detailed transfer function block diagram, but I will start off with the second equation. You could easily start with the first equation and it will be quite obvious once. Okay, so of course the first step, when you approach this problem is to take the Laplace transform of the equation. In this case we start off with equation 2, so let's do that. Alright, so let's take the Laplace transform. Alright, if we do that we get m2 s squared x3 of s. We assume the initial conditions in this problem is 0. Alright, so plus b increment sx3 of s plus k2 x3 of s is equal to k2 x2 of s. Let's label this equation 3 just in case we need it. Okay, before I continue drawing this detailed transfer function block diagram, I want to point out something important. It's convention to avoid using improper transfer functions in a block diagram. If you recall, an improper transfer function is one in which the order of the numerator is greater than the denominator. What that means is we want to avoid using so-called differentiators, or in other words, a Laplace variable s as a transfer function. We rather want to use 1 over s, which is called an integrator block or an integrated transfer function, and which is this 1 over s is of course a strictly proper transfer function. Okay, so keeping this in mind, I will start off like this. I know the highest order of the derivative in my model, in this case the equation 2, is 2. Okay, so I will use 2 integrator blocks in series like this. Okay, I need to bear my space in mind because this is going to get the detailed transfer function block diagram. Okay, let's start on the right hand side here. So I'm going to draw 2 integrator blocks, 1 over s, 1 over s. Okay. I'm going to label this signal x3 of s. So this signal here is x squared, not x squared, sx3. Okay, I'm going to avoid using the x of s, just sx3 to save space. And then this signal is x squared x3. Alright, this is quite obvious because if you look at this, this is what is on the output here is 1 over s times sx3, and that is of course just x3. What is on the output here is 1 over s times sx s squared x3. Alright, so that is of course then just sx3. Alright. Next, I will solve my equation or equation 3 for s squared x3 of s, as this is a signal on the left hand side of this integrated blocks. Alright, if we do that, I'm going to move down over here because I want to draw my transfer function block over here. So I'm going to move down. If we solve that for s squared, if we solve this equation for s squared x3, we get so x squared x3 of s is then equal to 1 over m2 times minus the increment s x3 of s minus k2 x3 of s plus k2 x2 of s. Alright, so this equation can be interpreted like this. What it says is that the signal s squared x3 of s is equal to 1 over n2 times this whole term. And this whole term is just a sum of signals times transfer functions. Okay. So we can modify our diagram like this. Remember, here is s x3 of s. Alright. So if we modify our diagram, we can say that, alright, here must be 1 over m2. I'm going to have to save some more space here. 1 over m 1 over m2 times this sum of signals. Alright. Remember, multiplication is just two transfer functions in series, so that's why you can draw them in series. Okay. But remember, this is a sum of signals, so we use to represent a sum, we use a summation block, so we can modify a diagram like that. So that's a summing junction. Okay. So now looking at this summing term, we can read off and see what needs to be summed into that summing junction. Let's take this term first. All right. We can see that this term needs to go into that summing junction. So that says that the signal x2 needs to be multiplied by k2. All right. There's no signal x2 in here, so we can define this like this. Let's do it like this. So we call this signal, we can draw it k2, and what needs to be multiplied by k2 is the signal x2. Okay. So at the moment, what's on the output there is x2, k2 times x2. Looking at the next term, we can see that we need to add the signal x3 times minus k2. All right, but we've already got the signal x3 defined in our diagram or in our block diagram, and here it is. Okay, so we can just branch our signal off from there and multiply that by minus k2. So let's do it like this. Okay, I need to. Oh. All right. We still have a term left, and we see that that term says that we need to add the signal x3 times minus b increment, and we've got, the signal s x3 times minus b increment. We've already got the signal sx3 defined in our diagram, so we can branch it off from here and multiply it by minus b increment and just add it to the summing block. Alright, and that completes the diagram for our first or second equation. Okay, I will move this for space. I'm going to move it over here. Okay. In a similar way, we can do this for the first equation. If we start, remember we have to take the Laplace transform of that equation as well. So let's start at the bottom here. So that will be m1 s squared x2 of s plus b1 s x2 of s plus k1 plus k2 x2 of s is equal to k1 x1 of s plus k2 x3 of s. Okay. Again, I know the highest order of the derivative in my model is 2, so I will again use two integrator blocks in series like this. So let's, guys, I'm going to have to move this down a bit. Okay, so I'm going to use two integrator blocks again in series. And I will define this signal as x2. So this signal will become sx2, and this signal will become s squared x2. Again, this output is 1 over s times sx2, so that's just x2, and this output is 1 over s times s squared x2, and that just becomes sx2. So I have in this model, I have as output x2, but in this model I have the input as x2. Alright, so that means I can just, those are common signals, so I can just easily connect those two. Let's move that over. Delete the one and connect the signal. Okay. Next I will solve again this model for s squared x2, as this is the signal there. Alright. If we do that, we get s squared x2 of s is equal to 1 over m1. That becomes minus b1 sx of s minus k1 plus k2 x of s plus k1 x1 of s plus k2 x3 of s. Okay. Again, this equation can be interpreted like this. It says that the signal s squared x2 is equal to 1 over m times this whole term. Okay. So again, I can just draw it like this. So this is 1 over m1, and we've got some summation block. So this is 1 over m1 times some sum of signals. Here we've got 1 over m1 times sum of signals. All right. So if you look at this sum of signals times transfer functions, we can see there's a few terms that needs to be summed into the summing junction. Let's start off with this signal, because we haven't got x1, the signal x1 defined in our system or in our block diagram. So let's draw it like this. That will be K1 times the signal x1, and that will be a positive. All right. The next signal that we can use or look at is this one. So that says we need to take the signal x3 of S and multiply it by K2. Of course, from the first diagram, we already have the signal x3. It's over here. So we can branch it off from there and just multiply that signal by K2 and sum it into the summing junction. It's a horrible line. Okay. Next we see that we've got minus K1 plus K2 times X. That should be 2. This should also be 2. Alright, so we've already got X2 of S, here it is, the signal x2 of S, and we just need to multiply that by minus K1 plus K2. And we can do it like this. And then our final term is that term, and it says we need to multiply the signal Sx2 of S by minus B1, and of course here is X or Sx2, and we need to multiply that signal by minus B1. Okay, and that completes our detailed transfer function block diagram for question 3a. This video is getting a little bit long, so I'm going to stop here. You can do transfer function block diagram algebra on this to reduce it to a single transfer function block, and that's what you're going to have to use for doing question 3b. If you would like me to do a video on question 3b and even question 4, please let me know. I'll try and open a forum or something so that you can post some questions and ask me to maybe do question 3b and question 4. Alright guys, good luck with the test.